I hope you all had a good lunch. To begin this session, I'm going to have Christian Gaetz, who will tell us about the one scales and posets of Bruhat integral polytopes.
Good morning. And thank you all for coming. This has been an interesting conference so far. Hopefully, what I'm going to tell you about, I started from a combinatorial perspective, but hopefully there's some connections to several different areas of interest on the audience. So I'm going to talk about one scales and posets of Bruhat integral polytopes. I'll tell you what I mean by both of those things, starting with Bruhat integral polytopes. Okay, so Bruhat order is a partial order on the set of all permutations that I have. So it's a partial order on the symmetric group. I'll show you a picture on the next slide, which is maybe the best thing if you're not so familiar with this. But here, length L denotes the number of inversions of a permutation. So I look at a permutation in one-line notation. I'm just counting pairs of numbers that are out of order. And going up in Bruhat order means I swap I and j on the condition that my length increases by 1. Equivalently, this length can be thought of as the fewest number of these adjacent transpositions I need to write my permutation. Okay, here's a picture. So on the left, this is for S3. The minimal elements of Bruhat order is always the identity permutation. The maximal element will always be this reverse permutation. And going up by one step is swapping. In this case, if I swap the 1 and the 3, that gives me the 2. And this is what it looks like on S4. So it's fairly complicated already in the case of S4. And this partial order shows up in a lot of combinatorics, a lot of algebraic geometry related to things like sugar variety. The context we're going to be interested in is Bruhat integral polytopes. So I'll write U brackets V just for the set of all permutations W, which lie in between U and V in Bruhat order. And then following the definition of Benama and Williams, the Bruhat integral polytope, Q sub UV, is just the convex hull of all the permutations in this interval, where I view a permutation as a vector. So the permutation 3, 1, 2, I just mean first coordinate 3, second coordinate 1, third coordinate 2. So all of these permutations are exactly the vertices of this polytope. So as an example, which might be the most familiar to people, if U is the identity permutation and V is, I'll write W naught for this longest reversed permutation, then this Bruhat interval is in fact the whole symmetric group. So I'm taking the convex hull of all permutations, and that's a very well-studied object called the permutohedra, which is shown here. So I guess that's oriented sort of sideways in this case, but here's the identity permutation, here's the reversed one, and this is an interesting polytope. So you'll notice, if you look at the edges of this polytope, the edges, if I think of this as the bottom and this as the top, is actually a different partial order on the symmetric group than the one we started with. Here, I only have edges when the values I'm swapping, so here I swap the 2 and the 3 to get here, are adjacent. So swapping the values I and I plus 1. So that's something called the weak Bruhat order, which is, from our perspective, will be kind of the opposite of extreme of the Bruhat order we started. Okay, so just before we get into the details of what I want to talk about, I want to say a few contexts where this polytope, these polytopes have arisen that might be of interest to various subsets of the audience. So this polytope is the moment map image of a generic torus orbit closure in a Richardson variety. So these are certain interesting toric varieties, if you like to think about toric varieties. And in particular, the vertices and edges and faces and so on of this polytope tell you things about the orbits, torus orbits in this interesting toric variety. It's also the moment map image of the totally non-negative part of this Richardson variety. So this comes up in the theory of total positivity of flight variety and its subvarieties. You can think of it as a Coxeter-Matroid polytope. So for people who like matroids, I guess this is a flag matroid polytope in the case of the symmetric group. And if you like generalizations of matroids to other Coxeter groups, it also applies in that case. I should say, for those in the audience who do like other finite Coxeter groups, everything I'm going to say has analogs there, and the theorems either are known to hold or are conjectured to hold, but for this talk I'm just going to talk in terms of the symmetric group. And if you're interested in those other things, you can fill in your head what the statement should say. Lastly, it's in a special case, it's isomorphic to something called the bridge polytope, which was introduced by Lauren. And in this case, paths between the bottom and top vertex along the one skeleton of the bridge polytope correspond to decompositions of certain plabic graphs called BCFW-bridge decompositions of plabic graphs. So those decompositions, I'll have one slide later about them, were introduced in the book of Nima et al., but I'll say a little bit more about that later. So what are some basic structural properties of these polytopes? So one of the most interesting structural properties is that any face of a Bruhat integral polytope is itself a Bruhat integral polytope. So if I look at my Bruhat integral polytope QUB and I take some face of it, that will be some Q U prime B prime. And in particular, if we just think of what that says for edges, so an edge of this polytope has to be a one-dimensional Bruhat integral polytope. In other words, it just has to be a cover relation in Bruhat order. This fact is actually equivalent to this one here, that these polytopes are something called generalized polytope. So what does that mean? Here is an apparently very blurry picture of, this is the grade arrangement for type A3. So this is the set of all hyperplanes xi equals xj. Being a generalized permutohedron, so the permutohedron, the polytope we saw earlier, its normal fan looks like this. Any polytope whose normal fan coarsens this one is called a generalized permutohedron. So what that means is, if you look at your polytope and you look at the normal fan, it will be obtained by removing some of these panels here so that the cones are actually unions of several of these cones here. Now these cones are in bijection with permutations, so another way of saying that is the normal fan of the Bruhat integral polytopes at the fan corresponding to each vertex will have a set of permutations associated to it. That is the set of these cones that get merged together in its normal fan. Okay, so the property of Bruhat integral polytopes that I want to study is their one skeleton, and in particular, sort of by analogy with the permutohedron, where we could view its one skeleton as a partially ordered set, and we got weak order. I want to do the same thing here. So what we're going to be interested in, I'll denote PUV. This is the partially ordered set on whose elements are this interval, but I'm not going to use all of the cover relations from Bruhat order as before. Instead, I'm going to only use those if you're actually an edge in my polytope. Okay, I'll show a picture on the next slide. So the result of that we saw earlier, that all edges of this polytope are in fact Bruhat cover relations. We're going to use that, we're going to say, look at the poset where I only take those cover relations as defining my order. So as before, we saw that if we have the entire symmetric group, the case when the polytope is the entire permutohedron, this partial order is what I was calling the weak order before, where we only have adjacent swaps giving order relation.
Question.
Yes?
Do you need the condition length of y equals length of x plus 1?
No, that's implied. That's a good point. So one thing I do want to, so this is implied, but in particular, this poset has the same rank structure as usual Bruhat order. It's just weaker. Okay. Other questions? Okay, let me show you a picture. So this is a case. So U is the identity permutation at the bottom. V is this permutation 3, 4, 1, 2. This, if you view the bolded black edges in the foreground and the gray ones in the background, you should be able to see this as a three-dimensional polytope. But I'm also doing this just as a partially ordered set. So this at the bottom, these things above it, and this is my top element. So what's true is that this poset is intermediate in strength between the weak order and the Bruhat order. So if you have an adjacent swap, that will correspond to an edge here. But there are some extra edges, which are not adjacent, coming from...
You have two elements labeled 3, 1, 4, 2.
Uh-oh. Okay. Exercises to figure out which permutation I missed. Thank you for catching that. I redo this picture at one point. Apparently, didn't label it correctly. Which one am I missing? 3. No. Exercise. There you go. No, it should be
1, 3, 4, 2.
No, it's here. Okay, so it should have length 3.
Oh.
2, 4, 1, 3. Okay. Good catch. All right. So one thing, maybe it's a spurious observation right away, but if you look at this poset, it's actually a lattice in the ordered theoretic sense. So what do I mean by that? I mean, if you take any two elements here, so say this element 2, 1, 4, 3, and this element 1, 3, 2, 4, they have a unique minimal upper bound, this element up here. That is, there's a unique element such that if you are bigger than this and you are bigger than this, you must be bigger than this guy. And similarly, there are meets, so greatest lower bounds. So if I take a pair of elements, there is a meet such that if you're below both elements, you must be below that element. So the weak order, the case where we took the entire permutohedron, that poset is known to be a lattice, and we're going to investigate that property for these more general purpose polytopes. That's going to end up leading to some interesting facts about H vectors and so on. Okay, questions about this picture? So the colors, I have not explained the colors yet. Those are colors.
It's always n-dimensional or sometimes lower dimensional?
Yeah, that's a good question. So it should always be, I guess, n-1 dimensional, assuming my permutation had sort of full support. If I live in some parabolic, then it will be smaller, but certainly generically it's n-1 dimensional.
I have a quick question.
Yes?
I see that the purple vertex has valence 4, which makes this, I guess, not a simple polytope.
Yeah, this is not a simple polytope. So it's an important difference between this polytope and the permutohedron itself. But later on we'll see that these polytopes behave in some ways as if they're interesting. So thank you for asking. Okay, let me move on. So first, what this is saying, so we're thinking about this poset. This is saying my poset that I care about is really a quotient of the weak order by some equivalence. So if you remember before, our normal fan is going to coarsen the braid arrangement, so I'm going to be identifying some permutations together as a class. This is saying that if I take the quotient of the weak order with respect to that equivalence, I get the poset I care about. Now this one actually has to be slightly careful here because this equivalence is not what's called order congruence or lattice congruence. So in principle, I'm not allowed to just take a quotient of a poset by any equivalence I like. I might not end up with a poset. So there's content to saying that this is in fact a poset and this is the poset I want. So this is somewhat a strange thing. And we have a lattice. As we'll see later, we take a quotient of it and we end up with a lattice, but it's not what's called a lattice quotient. And for those who know what this is, each equivalence class under this equivalence relation has a unique minimal element. I'll show some pictures later. And for those who know this terminology, that's the matroid map. That's taking a permutation to its minimal representative. Okay, so here I will now explain these colors. So this is an illustration of the previous theorem. On the left is the entire weak order. I have colored in some equivalence classes corresponding to which permutations get identified together in the normal fam. This is the equivalence relation theta from the previous slide. And then I'm claiming this poset is the quotient of this partial order by this equivalence class, meaning a node in here is less than another if there is something in its equivalence class which is less than something in the other. So let's see, what's the non-trivial example? So let's look at purple and orange. So purple is less than orange here because some element of the purple equivalence class, say 4231, is less than some element of the orange one, say 4321. But it's not the case that every element is less than every element. For example, this 3142 is not less than 3412. So that's what I mean by quotient. And if you map colors to colors, you get this picture. We're collapsing all the classes to a single. Questions about this statement? Okay, so we have the statement that we can understand this partial order by viewing it as a quotient of this other partial order, but that on itself, because this quotient is not nice, as I was saying, it's not a lattice quotient, it doesn't tell us that, for example, we always get a lattice. So we have to think a little bit more carefully about these equivalence classes. So everything I'm going to say from this point on, I'll be assuming that the bottom element is the identity, but the top element is arbitrary. So I was saying before that each equivalence class, so this denotes the equivalence class of X, all the things the same color as X in the previous picture, contains a unique minimal element, but it also contains a unique maximal element, and that's not at all obvious. So in this picture, if I look at all my color classes, say the orange class contains a unique minimal element, but it also contains a unique maximal element. So that's the first fact, and I'll write top of X for that top element of the equivalence class of X. So that's the first important fact. And the second important fact, so here's another example showing minimal and maximal elements. The second important fact will be that this top map preserves the weak order. So what do I mean by that? I mean, if A is less than B in weak order, and I map A to the top of its equivalence class and B to the top of its equivalence class, the one will still be less than the other. So for example, 3124 is less than 3241, and I can map this element to the top of its equivalence class, which is right here, and it will be less than the top of the equivalence, the green equivalence class. But it's not true that the bottom map respects this order. For example, again, 3214 is bigger than 3124, but it's not true that this bottom element here is bigger than this bottom element. Okay. So the top map, the one which was not obvious that it existed, is the one which plays nicely with respect to weak order. And this is what's going to establish the order theoretic property we're interested in.
How explicitly do you understand those classes? I think you defined those classes in terms of what, the normal fan?
Right, yeah, so actually not at all that explicitly, and that's one of my current proof that the top map respects the order is not very explicit, and something I'm working on making more combinatorial is to understand if I give you an element, what is the top of its equivalence class. That's not very explicit right now. Okay, so this actually proves the observation earlier about that these posets seem to be lattices, because we can get the join operation. So this V here, that's the notation for the join, the least upper bound of two elements. If I want to compute the least upper bound in my poset, what I can do is take the top elements of the two equivalence classes. These no longer live in my Bruhat interval, but they live in the weak order overall. I can take the join there, because we already know the weak order is a lattice, and then I can take the bottom map and push it back into our Bruhat interval, and the claim is that that defines the lattice operation in this case. So even though we are taking this thing is not a lattice quotient, the fact that we have at least this property implies that we get a lattice. I should say, I don't know a good description of the mean in this poset. So this is actually slightly technical. EV is a joined semi-lattice quotient, but not a lattice quotient of weak order. In particular, it doesn't inherit lattice theoretic properties of weak order, like being semi-distributed. So just a couple special cases. If we say, just look at the join of all atoms. So atoms of a poset are all of the elements which are immediately above the minimal element. So I take a subset of those. In those cases, those are simple reflections. So those are the permutations, just swap by an I plus 1. I ask, what is a join of a set of those? This ends up recovering the results of these authors, that there's a unique longest element of, this is the subgroup of the symmetric group those elements generate, which lies in our Bruhat interval. So this join just recovers what they call the characteristic map. To give an example again, when V is Grassmannian, and as I said before, this poset, this polytope, ends up being isomorphic to a bridge polytope. Fraser conjectured, or at least he conjectures that this was a lattice, so a special case of the previous theorem confirms what he had thought. And in this case, there is a connection to plabic graphs. So there's something called BCFW-bridge decomposition, which were introduced by these authors. What they are is a recipe for building a plabic graph for a certain cell in the fully nothing corresponding. So plabic graphs, we have seen various flavors of planar embedded graphs and disks in this conference. Plabic graphs are another version of those. Sometimes we're related to on-shell diagrams. But given any plabic graph, one can get a permutation by following what's called the rules of the road. So if you start at a number, you turn left at white vertices and right at black vertices, you get a permutation. But it's not completely obvious if I give you a permutation how to write down a plabic graph with that chirp permutation. So that problem is solved by these bridge decompositions. And Lauren, in a very nice paper, showed that bridge decompositions of a permutation are nothing but paths from the bottom to the top in a polytope which is isomorphic to a Bruhat interval polytope. So for example, in this case, if I took this path and I paid attention at each step to which numbers I'm swapping 1 and 2, and then 2 and 3, and then 1 and 2, and then 2 and 4, those correspond to these bridges. 1 and 2, 2 and 3, and 1 and 2 again, and then 2. So, in some sense, there's an analogy between these bridge decompositions of plabic graphs and reduced decompositions of permutations. So this is, in fact, Lauren's paper is called the positive analog of the polyhedron, and one of her reasons for calling it analog is that property. So,
Sorry, every path up corresponds to a way of doing a bridge decomposition?
yes, yep, and vice versa. The bridge decompositions are exactly the paths. So just as the permutohedron, or the weak order, which encoded reduced words, is a lattice, so the poset, which encodes bridge decompositions, is also a lattice. So I guess this extends the analogy between those two polytopes. Okay, any questions before I move on to a slightly different set of implications of the fact that the top map preserves weak order will also give us some implications about H vectors, which is what I'll move to next. Yes.
When you restrict it to the first permutation being the identity, is that because these results break when you do other permutations, or?
Yeah, so the one skeleton is not necessarily a lattice for general pairs. I think the first counterexample is in S5, so if it wasn't for my computer, I wouldn't have found it. You have to go to a fairly messy example to find it, but it breaks in general pairs.
Do you know how to cut these polytopes out with inequalities?
They're in Williams and Zuckerman's paper. They do give some inequalities for how to cut these out. In general, there are rules telling you what the faces are, what the inequalities are, and so on. I think some of them are still can probably be made more explicit with some combinatorial work, but yeah, I'm still thinking about that sort of thing. But there are no descriptions of how to cut it.
I'm sorry, you said this probably early on, but the normal fan of this guy is a portioning of the. This is a generalized permutation or not?
This is a generalized permutation, and yeah, so these equivalence classes I was drawing are exactly which cones get glued together in the normal. Yep. Any other questions? Okay, so now I want to talk a little bit about how these polytopes behave in some ways as if they were simple. Okay, so first maybe I should just remind those who don't think about polytopes every day that a simple polytope, if I have a d-dimensional polytope, it's simple if around every vertex there are d incident edges, so the fewest possible number of edges incident to each vertex. This definition here is extending a slightly different characterization of simple polytope. So another equivalent way to define a simple polytope says, if I look at each vertex and I look at all of the edges emanating out from it, for any subset of those edges, there is a face containing exactly that set of edges. So this definition here is sort of extending that characterization of simple polytopes. And the idea here, if one doesn't want to try to parse the slide, is that I've got a vertex, it's incident to some edges, and we have a distinguished direction we care about. And I'm only going to enforce the condition I just said on edges which are emanating in that direction from the vertex. So I say I'm directionally simple with respect to this direction if for every vertex I look at the edges emanating out from the vertex which prefer that direction, and I require that every subset of those defines a face of my polytope. So that's what's said on this slide, and probably too much notation. Okay, questions about what that definition means?
So that depends on what direction.
It depends on the direction. That's right. Okay, so here's a theorem. So there, this follows from the earlier result that the top map respects weak order. There's a different proof of this theorem by these authors in the case of the symmetric group, which I hadn't been aware of, but recently realized that they already knew this in type A. But this polytope is directionally simple if we orient the edges as if the direction we care about is the upward direction in these pictures. Okay, so this was noticed earlier that this thing is almost simple. But for example, this purple vertex, which is not simple, is not going to be a problem for us because it has only one upward edge. So there's good. Whereas, for example, this bottom vertex has several upward edges, but it's simple around here. Every subset of these does define a face. And so this polytope will be directionally simple in general. So one combinatorial consequence of this has to do with the h vector. So normally for a polytope in the dimensions, the f vector, f0, f1, so on, fi counts the number of I-dimensional faces of the polytope. So f0 is the number of vertices, f1 the number of edges, so on. There's a transformation of that, which is called the h vector, which is defined by this identity. Oftentimes, one only considers the h vector when one has a simple, or if you're working in the dual setup, a simplicial polytope. So generally speaking, these are only nice to consider in those cases because of this theorem here, that if Q is a simple polytope, this h vector, these numbers are positive, and they form a symmetric and uninormal sequence. So I guess this is a very early instance, perhaps, of what Federico was talking about, where we have some sequence which has nice combinatorial properties, and in fact, if you think about why it has these properties, one has led to some interesting algebra and geometry. But yeah, usually these numbers are not nice, or not even thought about for non-simple polytopes. But a consequence of the upper simple property is that these h vectors still do have an interpretation, and in particular, they still are positive. So the h vector, it can be described via this top map. It's just counting the descent, the tops of the equivalence classes by their number of descents. So for example, in the case of the entire permutohedron, each equivalence class is trivial, so top of x is always just x. And it's well known that the h vector of the permutohedron is given by Eulerian numbers. How many permutations are there with a given number of descents? Here we have the same statement, but you have to map each x to the top of its equivalence class before you measure the number of descents. So in particular, these numbers are all positive, which is sort of unusual for a non-simple polytope. And they have this nice interpretation. I should say, for those who care about toric varieties, in type A, these actually end up being the Betti numbers of the toric variety associated to polytope, which again is strange because it's not a simple polytope, so this is not a smooth toric variety, and yet it's Betti numbers in this. That's definitely known in type A by work with those other authors, and I believe it's true in other types. It's subject to ongoing